So somewhere around here in example 1, when we studied the Euclidean norm, that was the case p equals 2, I said that now we have two different directions of generalization. The first direction was to introduce all these little p's here and go away from the 2 norm to other norms like 3 norm or 7.5 norm or something. We could even send p to infinity. Now a completely different direction of generalization is to make our vectors infinitely long. We could try the same expressions but now for infinitely long vectors, and that's what will happen now. So I think this is worth a new example. So this is then example 2. We don't know how to name these spaces. I'm not starting with x equal whatever. Rather than that, let me start with my little vectors. So they look like this: x1, x2, x3, and so on. And the entries are real or complex valued, and the norm could be defined just like we did before. So let's now already take the p norm of modulus x1 to the power p plus modulus x2 to the power p, and so on. Alright, so we could again call this the p norm, and we are assuming that 1 less than or equal to p less than infinity for this. Or we could take the infinity norm as the corresponding expression, which would then be maximum of modulus x1, modulus x2, and so on. And because this is now an infinite sequence, it's not so clear whether the maximum exists, right? So you know that for infinite sequences you could have a behavior like that you come closer and closer to the maximum, but you never reach it. In which case you wouldn't call it a maximum, you would call it a supremum. So the proper thing to put here now is supremum. Okay. So these infinite vectors here are often just called sequences. But if you say infinite vector, I'm also fine with that. And the spaces they live in, so now there comes capital X, are usually denoted by a little curly L, and then you write P here as an exponent, you just call it LP. And define it as the set of all of these sequences. And well, for sequences, we then like to write them like this, where the P norm exists and is a finite number. Now this leads to a new kind of problem, because before, when our vectors were still finite, we never had to worry about the existence of the P norm. But now what you can see here is a series, right? So this is now analysis. So this is the pth root of series I equals 1 to infinity xi to the power of p, and you have to make sure this converges, and that's what you do by this condition here. We can use the same condition for the case where p equals infinity, so we could just say here we do this for p including infinity, so the space L infinity. So L infinity is then the set of all bounded sequences x1, x2, and so on, because the fact that the supremum shall be finite means it's a bounded sequence, right? So we used to say bounded sequences in analysis 1, now we say L infinity. Sounds a lot more technical, but still the same thing. Now the astonishing fact is that every LP is a vector space, and this is not so obvious, not obvious at all, because, well, for example, this is saying that the sum of two L2 vectors is again an L2 vector, and checking that is tricky business. It's not so difficult for L infinity that the sum of two bounded sequences is still a bounded sequence. I think we can all agree with that, but not so clear anymore for P less than infinity. Still, it's true. And the norm that we have been introducing here indeed turns out to be a norm. So this is a norm, so it has properties 1, 2, and 3. We did check this for finite vectors in example 1, still true for infinite vectors in example 2. Talking about sequence spaces, as we call them, or spaces of infinite vectors if you want, let's introduce some more here. One other famous sequence space is denoted by little c and then sub 0, and that is the set of all such sequences x1, x2, and so on, for which the entries converge to 0. So these are the null sequences, or the whatever you want to call them. And again, the sum of two null sequences is a null sequence. Alpha times a null sequence is a null sequence. So also this turns out to be a vector space. Also a vector space. And there is a little brother of C0, and we call that one C00. These are the null sequences that go to 0 especially fast, in the following sense. The entries are 0 after a finite number of possibly non-zero entries. So that's the set of sequences x1, x2, and so on, with the property that only finitely many xn are non-zero. Right. So it's quite clear that C00 is part of C0, right? So if your sequence is eventually 0 after one entry, then it's clearly convergent to 0. So this is clear. Maybe it's not so clear how these two spaces are connected to the other ones, the LP spaces. Let's find it out. So I'm claiming that the rest of spaces is a somehow nested sequence, so they are contained one in another in the following order. So not so clear, but still true. C00 is probably the smallest of them all, is contained in L1. And then as P gets bigger, the space gets bigger. So let me say this is contained in LP and this is contained in LQ, where P is less than Q. And they're all contained in C0, and this again is contained in L infinity. So this Q is here less than infinity. Not so clear, and that's why it's an exercise problem. It's in fact on sheet 2. I think it's problem 1 or something, or in the total numbering it's probably problem 8 also. So if you want, you can think about it already now, but at least in about 4 or 5 weeks from now I will ask you to think about it. Okay, so just to complete this, let's make the one little drawing here of this nested sequence of spaces. So the biggest of them all is L infinity, and then somewhere in L infinity you have the set of all null sequences. So L infinity are the bounded sequences, right? So these are the null sequences, and then inside you have all the LP spaces. So for example, maybe this is L1000 and well, whatever you want. So there is L2 and L1, and then here this tiny thing inside is C00. The sequence is that only have finitely many non-zero entries, and then the rest is all zeros. It's easy to find examples of elements that are bounded, of sequences that are bounded but not null sequences, like this one, 1, 1, 1, and so on. It's a bounded sequence, so it's in L infinity, but it's not in the others. Okay, well here you have 1, 1, and then all the rest is 0. This would be in C00, and then, well, it's a bit more tricky to find elements in these sets here in between that are in one but not in the next level of sets, but let's worry about this at some later point. Now finally, and this is the last thing we're going to do today, we are looking at spaces of functions that are closely connected to the sequence spaces we've been looking at right now. So again, you take a parameter p, which is playing the same role as before, and for the moment let's take it less than infinity, and you take an interval, let's say from a to b on the real axis, and you look at functions f from this interval into, let's say, the real numbers, but not just any functions, but functions that have something to do with this parameter p. And the something is that you want the integral from a to b over modulus f of x to the pth power dx to be finite. So you could as well say that you want the pth root of this whole thing to be finite, which happens at the same time, of course. And then you could again call this the p norm, but now of the function f and not of a vector x. So you can see this is the very same construction as before. Before you've been adding over all the data of your vector x, And now you're adding over all the data of your function f, and because there's a lot more data in an interval on the real line, you need an integral instead of a summation, but otherwise it's just the same. In the same style, you would say that the infinity norm of such a function is just the supremum of its function values, modulus of the function values, when x is running through the interval from a to b. Okay, and then instead of the spaces little lp, now you have big or capital LP, and you say it over which interval, and define it as the set of all functions f from this interval into the real numbers, where the p norm that we just defined exists and is finite. So the construction is just like before. The only thing that changed is now you've got functions instead of sequences or infinite vectors, and that's why you take integrals. Okay, if you want to check whether or not this is a norm, you have to be a bit more careful, and in particular you will probably find that some of your functions give you a norm 0 without being 0. I mean, it's if somewhere on your interval AB the function is not 0, but in every other point it is 0, then I think that integral will give you 0, although it's obviously not the 0 function. So you get some runaways like this, and what you have to do is a bit technical. You have to put them all in a class and factor it out. My suggestion is not to worry too much about these things. If you take a class on measure theory and on Lebesgue integration, then you will do all of this properly. Lebesgue integration means that this integral is actually not meant to be the usual Riemann integral, but one of its generalization, which is the so-called Lebesgue integral, named after French mathematician Lebesgue. If the Riemann integral exists, then they both give you the same result, but sometimes Lebesgue exists and Riemann doesn't exist. Okay, just for completeness, let's recall one more class here, one more space of functions, and then we have it. Okay, so C over AB, and we had that in the very first lesson or lecture, is the set of functions f from AB into the real numbers where f is continuous. So this C here is for continuous. Okay. Again, all of these sets turn out to be vector spaces. So if you add two of their elements, you get another element from the same class, right? So the sum of two continuous functions is a continuous function, and so on. And if you equip them with the right norm, you get a normed space. So what's the right norm for the set of continuous functions? Well, you could work with all of these norms that we saw here. We will discuss with which norm it has good properties, with which norm it has not so good properties. But let's keep this for next time. Okay, that's it for today.